Welcome all to this webinar organized by Kerala Theoretical Physics Initiative. Kerala Theoretical Physics Initiative is a collective of faculties, postdoctoral fellows, and PhD students across the globe who are originally from Kerala. KTPI aims to create a home for research and education in the physical sciences by focusing on theoretical approaches. Our goal is to establish a research-friendly atmosphere at the undergraduate and postgraduate levels in Kerala. We are planning to achieve this goal by fostering strong collaboration among ourselves and with the colleges in Kerala. Today we have a very special speaker, Dr. Sreejith. He is going to discuss about India's very remarkable solar mission called Aditya L1. Dr. Sreejith did his bachelor's degree in physics from Calicut University, Kerala, and master's in physics from IIT Madras, Chennai. And then later he joined the Space Astronomy Group of UR Rao Satellite Center, ISRO Bangalore, as Junior Research Fellow. During this period, he worked on India's first dedicated astronomy satellite called AstroSat. He completed his PhD from the same group in the field of solar physics. After his PhD, he joined Trinity College Dublin, Ireland, as a postdoctoral research associate. In 2017, he joined the Inter-University Center for Astronomy and Astrophysics, IUCAA, Pune, as a research associate. From 2021 onwards, he is working as an assistant professor at the Manipal Center for Natural Sciences. He is also the project scientist in the team that developed the Solar Ultraviolet Imaging Telescope onboard Aditya L1 mission. Dr. Sreejith's research interests are astrophysics, solar physics, and space science instrument development. Okay. Dr. Sreejith, we are very happy to have you here. Thank you for your time. Over to you.
Thank you, Ratul, for the introduction. So though this is happy to be part of this, giving a talk here in this group. When Joe told me about this, I was a bit worried because I'm not a really theoretical physics person. Rather, I'm a bit far away from theoretical physics. I do mostly observations and instrumentation and part of modeling a little bit, but not hardcore theoretician, so-called theoretician. So I'm sorry if I didn't really touch upon the theoretician's problems here. I will be mostly giving you a brief gist of what Aditya L1, what science problems we are planning to address, etc. Definitely, we can have a discussion at the end. There's a lot which theoretical physics people can contribute to the field of solar physics. Of course, we can discuss that at some point, though I may not really cover that part in the talk. That is itself is a different topic of talk as such, because it will take another quite long time to discuss that. So I'll be talking about Aditya L1, India's first dedicated space observatory to study the sun. And I have to talk about sun because sun is also our nearest star, like any other star. So I belong to a place called Manipal Center for Natural Sciences. Just now Ratul was asking me about that. It's a new research center supported, like a research institute supported by Manipal group or Manipal University. So we are an all research center. I just give you a brief thing about our group because since Ratul was asking, we are having a good astrophysics research group here right now. We cover, there are faculties who study all the way from heliosphere to galactic sources, UV astronomy, and also extragalactic sources like AGNs and galaxy clusters. And there is also a good cosmology group here. We study on the inflations and 21 centimeter line coming from the early universe. So we have a very active PhD program, which is we are having many PhD students now. We also have started recently an integrated MSc PhD program, which is for BSc, BTech students. So any of you, if there are any students here who are interested to do a PhD in MSc and PhD in 5 years, you are welcome. You can visit our page and see our faculty strength and who are all working here, etc. Also, I would like to place here a open invitation for all of you to visit us, since we are very bordering to Kerala. So from Kerala border to here is around 70 kilometers, 70, 80 kilometers near Mangalore. So, after Mangalore, there's Udupi. We are in the Udupi Municipal Corporation. So all of you who comes to northern part of Kerala are most welcome to visit us, discuss with us, and maybe stay here for a few days and have some discussion on interesting science, which different people are doing here. Okay, with that brief introduction from where I belongs to right now, I'll directly go to the topic of the discussion today, which is on Aditya L1. As you all know, I'm sure in this group there will be people who are not astronomers or astrophysics people. There will be people from different fields of physics. So if I say astronomy is the cradle of physics, there may be, I'm sure, many people raising their eyebrows. But if you logically think about a time when human beings were, or Homo sapiens, may not be human beings as such, were hunter-gatherers who were working in the forest, hunting and living. One of the first scientific thinking or the curiosity which should have arisen in their minds of that time, maybe 50,000 years before or before, is how this day-night is happening. How is sometimes the sun is coming up, it is becoming hot. You can see everything, then it becomes night, you cannot see things, where all the wild animals starts coming out. And as the night comes, you see the beautiful sky. Definitely that time sky would have been much more beautiful and clean, because the atmosphere would have been much more transparent, obviously, or most probably, we don't know. But they would have noticed these beautiful things on the sky, which is repeating over time. They would have started noticing the patterns. So from very, very early stages of our evolution, the curiosity, which we call the science now, or systematic study of certain patterns which is appearing in nature, would have started with looking at the skies. Hence, I can confidently argue here that definitely astronomy should be the cradle of physics. And you know that even now it's one of the, if you talk to kids, one of the most topic which brings them, or which arise curiosity in them, is astrophysics. So from the birth, a mother starts showing the moon and the stars. That's when the brain start becoming curious about things around the world, or in the nature. And ancient astronomers, astronomy is so ancient as human history, civilization is involved. I don't want to spend a lot of time on that. Many of you might be knowing that. One important point I want to focus here is the sky. When you look through eyes, which you generally see, and the sky which so-called astronomers we study, are slightly different. It is the same region. You see, it's a globular cluster where you can see star forming region. You can see what you look at here, you will see is this. Whereas this is an image taken from Hubble, if I'm not wrong. You see it's really different. I'll touch upon this a little more in the coming slides. This is why I want to stress this point, is to bring you or convince you that these missions like Aditya is required. Because one of the common questions, which is very commonly heard, is why do we spend a lot of money, 400 crores of rupees, to send a satellite just to study the sun? So I just first want to make sure that you all are convinced that such missions are required for betterment of science and our understanding of the nature. And what we are talking today is about a small feature on the whole universe. Universe is so big, as this picture, artistical image shows. It's so vast and big. Our galaxy is such a small thing in the whole universe, and sun is something which is on a corner on the galaxy. We put my pointer here. Okay. Hope you can see my pointer, I don't know. Yeah. Sun is something on the Milky Way on the edge. It's a very normal medium-sized star. Nothing specific about Sun, or other than we live around. And when around Sun is a normal planet, there is bigger planets than Earth, smaller planets than Earth. There are planets with a lot of interesting features on solar system itself. So what we are going to talk about today is all the small fellow in the whole universe, which is called the Sun. Why do we are interested in the Sun, which is just a normal star in the universe? And the answer lies with what Galileo Galilei told. It is very interesting because with all the planets revolving around it and depending on it, can still ripen a bunch of grapes as if it had nothing else in the universe to do. It's a philosophical words from Galileo Galilei. If you think for some time, you'll realize that though Sun is just a star with all the thing, but in our livelihood, it's the most important star. Whatever happens in all other stars in the universe may not really affect us. It's just our curiosity. But whatever happening on the Sun will directly affect us. It depends on our food, it depends on our climate, it depends on our sleep, health, whatnot. Because of that, traditionally, you take any civilization in the world, let it be Indian civilization or let it be Inca Maya civilization, which is the current American countries, or the Mesopotamian civilization, the current Gulf countries, or even the European Greek civilization. Any civilization in the world you take, you will see a sun god. The prominent god there is sun. It's because, very obviously, because people realize that sun is so important in our life. And anything happening on the sun has a direct influence on our life. People realize this much early ages. And obviously, as we start, the things which influence us the most, or the people or things are in the nature which people fear about, people adore about, people respect about, they slowly become gods as usual. So there is obviously the sun god is. I just was trying to say is that from the beginning of civilization, you will see that people are very interested about studying the sun. But sun is special for us not because of its historical importance or anything. It's important, it's interesting, it's because it's our star, sort of, you can say. Though it's a normal middle-aged star, by middle-aged I mean, I'm telling this because I hope there is some non-astronomers here. Sun is of around 4.5 giga a year, and it will live another 4.5 giga a year or 5 giga a year. In astronomers' language, we call it its main sequence star of a spectral type G2. Okay, let's not go to the detail. Just understand that it's just a normal star in the universe. People who are interested in stars will consider it as a boring, normal, middle-aged star. There is nothing interesting in our life is like that, right? When we are boys or young, we are all jumping, bumbling. People will be all looking at you. When you're old, you become very, again, noticeable person in the family or society. Whereas middle-aged people are the boring stuff, right? So like me, or our age, my age. So sun is of such normal middle-aged star, which has nothing interesting if you look at the universe or the whole other stars in the skies. But it's interesting because it is our star. It's a very special star for us. It's the only star which we can resolve in spatial scales, and through which we can study the fundamental processes. This is an important point that if you see the history of astronomy or even now, every study about stars is connected or it is measured in terms of sun, because it's the only star in the sky with all this modern technology, evolution, everything. It's the only star where we can nicely resolve the surface. And by resolving the surface, we can study in detail what is happening on the surface of a star. It's impossible for any other stars in the universe. Whichever biggest telescope you use, all other stars will remain a dot with few pixels on your camera. That's it. You cannot study anything further than that by spatially resolving. whereas sun is the only star where you can spatially resolve. Hence, it's become very important for understanding the overall stellar structure or life of a star, etc. Also, to verify some of the theoretical models. Since there are a lot of theory interested enthusiasts in this group, hope you might know about the 2005 Nobel Prize, because the solar neutrino problem, the theoretical model of the sun was not matching with observations, the number of neutrinos coming from the sun. And there was a lot of debate whether it is a model problem or is it observational problem, which got resolved later. I don't want to diverge you to that, and which got solar neutrino problem, in fact, got 2 Nobel Prizes in 2 different times. What I'm trying to say is that to test the theories of stellar structure or how star form, one of the only source we have right now, or which we can resolve, is sun. Of course, you can verify from other stars these days using spectroscopy, spectropolarimetry, etc. But if somebody want to image it with good spatial resolution, we have only one candidate, which is the sun. Hence, it's important to study. It's also our star. Our planet is dependent on the sun. I already told about that, though not only us, the whole heliosphere is depending on the sun. And it almost provides all the energy to the sun. It's not about solar energy I'm talking about. Energy by which I mean our energy, our life. We are all alive now, or sitting here, hearing this talk, or I'm speaking because I had some food yesterday, today morning, day before yesterday. And that food supplied the energy to me, the glucose. And the food is created by plants or animals, or finally, it is all photosynthesis. All the food came from that. And it is the solar energy which is converted to eatables, edible glucose, which provides us energy. And it is also the one which provides the energy for the water vapor to rise, the rain, or anything you consider, it's the solar energy. I was telling this in a talk recently, and a student told me, no, you are wrong. There is something called nuclear energy, which is not depending on the sun, which is true, but in a way, but in another way, I can say it is also depending on the sun, because it's a different topic again. How did we have this big nucleus like uranium or thorium? All of them definitely would have come from sun. We would have the earth crust. All these things are there because it would have come from the sun. So it is in a way indirectly connected as well. So what I'm trying to say is that sun is very special for us because it has direct influence. Any activity on the sun will have effect on us. I'll come to that a little more in detail. And it's also a unique laboratory where we can study of various branches of physics. Suppose we want to study the fusion in astrophysical scales. Of course, there are these days fusion reactors being built in labs. People have successfully tried some of these fusion reactions on Earth in a very, very small scale, micro scale. But if we want to do in astrophysical scale studies, the only option we have is sun, because we can resolve it. So it is connected to multiple branches of science. You can see that from sun-Earth relations to cosmic ray studies, solar planet studies, some fundamental physics like neutrinos, gravitation, and plasma physics studies, people who study about turbulence, dynamos, and all of them have some or other connection with sun. A brief resume of the sun. Let's not go through all the numbers. I just highlighted some green, which are maybe of interest to you. The mass of the sun is almost, as you can see, around 3 lakh times Earth's mass. And the radius is almost 100 times Earth's radius. The size, just to give a scale of size. Okay. I think the other things are chemical composition is around 75% hydrogen and mostly helium remaining, and only 2% of other components, which goes all the way to very high elements. There is iron line. You can see even there is gold on sun. I was again, another student was asking me, is there gold on the sun? Is Aditya going to bring gold from sun? So I was telling her that definitely there is gold on the sun. People have observed gold on the sun using spectroscopy, but it is so small that nobody is interested to go and dig it out, and it is impossible to dig it out as well. Okay, so The real current solar physics, which we call for a systematic study of the sun, started with Galileo Galilei focusing his telescope to the sun and started marking whatever he see on the sun. Interestingly, what he saw was pimples on the sun god, which he beautifully reported, and the kings or the feudal lords of that time were really unhappy that Galileo found pimples on the sun god. But he drew these dark features on the sun. He thought it may be the region which is already the fire, the region where the fire is over, because he was comparing like a normal fire. But interestingly, this region was moving. One place it was seen on first day was not seen the next day. It was moved to other places. Shape changes, some of them appear, some of them disappear. And of course, he didn't know what it is. And most interestingly, Galileo did this observation in 1600s. As you know, he lived in 1600s. Almost for 300 years, up to 1900s, nobody knew really what exactly these black dots are. It was in the last century, the first decade of 1900, it was found what these things are known as sunspots. So the background is the image of a sunspot. The earth is just to give an idea for you about the size. Don't think there is an earth sitting there. That is just placed there to give an idea about the size of that, what we call as sunspots. It's so big when you compare to the size of Earth, and this is dark compared to the background. We now know that this is because of strong magnetic field here, and there is a lot of interesting plasma physics happening in this region. How magnetic field plasma interacts, and how magnetic field resists for plasma coming into this region, and hence it looks cold. It's a lot of interesting plasma physics or plasma magnetohydrodynamics which happens there. So many of the magnetohydrodynamic modeling and theoreticians, they use such observations or study of sunspots to verify many of their MHD models and their theoretical frameworks. Sun also rotates, as you can see. Since it is not a rigid body, it's a sort of differential rotation. So the center rotates faster. As you go to the pole, it rotates less because it's not a rigid body. And as it rotates, you see these magnetic fields coming on the top. What you see here is the black things are the southern pole of magnetic field, or the magnetic field entering inward, and the white are the positive magnetic field. So these are bipolar regions, whatever you see as positive and the black and white. And interestingly, you can see that always there's a pair of positive and negative. So that's another interesting thing, which a lot of theory studies are even now going on the dynamo process inside the sun. What is really happening inside a star through which these magnetic fields are created, magnetic fields are generated, it comes out and it dies off after some time, it degrades after some time. So there is a whole branch of theoretical physics studies happening on how these magnetic fields generate, sustain, the pattern of evolution, etc., etc. Interestingly, okay, this is the differential rotation I was talking about. Doppler measurement, basically. I think all of you are physics people here and know what Doppler shift is. So you see that there is a much higher velocity at the center, and as you go to the pole, it is much smaller. It's also interesting that you can see as the sunspot form and evolve, it emits a lot of rays. I'll come to a little more details about that. It causes something called solar flares, and I'm sure all of you would have heard about these solar flares, which is a sudden emission of a lot of energy from the sun to the skies. I'll come to that in the coming slides. So if you take a different telescope and start zooming in into the I think I should remove this thing. If you start zooming in into the sun surface, remove this pointer and click. Okay. Give me a moment. Let me just get rid of this pointer. Yeah. Okay. So if you just zoom into this small dot here, as the technology improved and we got better, bigger telescope, you start seeing more details of that. Just look at that for a moment. It was that small dot you saw earlier. Now it has become a lot of convective cells, and convection is a process of energy transfer. And as it's like boiling of water or a boiling of a very viscous fluid. If you have a viscous fluid boiling, you will start seeing such convective nature. It's again another plasma physics property which a lot of people are studying on these features. And wherever magnetic field is there, you start seeing such features. Interestingly, if you look further into this, you start seeing that there is much more features. And when I say features, you remember these are all very huge, big things with it's a plasma magnetic field interaction. There is a lot of interesting physics happening there on how magnetic field interact with plasma and create such features. So from here, it has come all the way to here. I just wanted to give you a brief idea about that. So the size of the small fellows which I showed here, which is a small hairy like feature, it's around 70 kilometers. 70 kilometers is almost the distance from Thrissur to Cochin. So much big this small feature. And what you see at the center is a dark feature, which is of, again, a lot of interest. And there is people studying about this, how plasma interacts with magnetic field, and these features are created. What does this mean? What is this dark line means in the middle, etc. So that's a different whole together branch of science which people are studying. And as I told earlier, this magnetic field has a pattern. It forms a 11-year cycle. So what you see on the x-axis is the time on the bottom graph, and y-axis is the area of the sunspot in terms of hemispherical area. And you can see that the number of sunspot is increasing and reducing over a 11-year cycle. But it has different heights, means it's still not clear why that it has different heights. And if you plot the same thing on a latitude on the sun with time, this is the latitude on the sun, it forms a very nice pattern. And that's called butterfly diagram because it looks like butterflies. It has nothing to do with butterfly assets. But what it means is if you take some region here, let me point again. If you take some point at some point, when the solar cycle starts, at the beginning of a solar cycle, at the bottom you can see, the sunspots appear at higher latitudes, around 30° north and south. And as it evolves and as the cycle ends, you see that all the sunspots would have come to the center or closer to the equator on the sun. And then again, next cycle begins, the new sunspots appear at the higher latitudes. So we people working in solar physics say a new cycle began by looking at a new sunspot coming up in the high latitudes. This again, a lot of studies are happening, very interesting physics there. But the real question is, why do I started with saying that I will talk about a little bit sun and how it's interesting, because people should not think that sun is something which we study every day, we see every day. It's studied from Galileo's times for 400 years. What is there to study any further? Why do we waste money on this? So that's why I wanted to impress you upon that there is a lot of interesting features on the sun, which is still not understood, which has a lot of academic and research curiosity, as well as industry curiosity. And I'll come why it is having industrial curiosity as well, for interest for the industries and governments. But the first question is, why do we need to study sun from space? Really, do we need to go to space to study the sun? You can see it from here every day, so bright and big. So the point is, though it is very, very bright, big, everything, there is certain things which we need to study. We have to go to space to study. The reason being, all the lights from the sky won't reach Earth because our atmosphere is opaque some of these things. So what is there on the y-axis gives the atmospheric opacity. I think you know what is opacity means. It is the amount of the light get attenuated as it moves on the atmosphere. That's why, and the x-axis is the wavelength of the electromagnetic waves. So those electromagnetic waves or the light, which has wavelength which is very high, very low wavelength or very high frequency, we call it very high energy photons, like gamma rays, X-rays, ultraviolet. They have 100% opacity. It's opaque. Atmosphere doesn't allow it to come inside. If you go further to this, like TVs and all, there is some of them produces something called Cherenkov radiations and all, which is a different topic. But whatever we study, the sun, whatever comes from the sun, or most of the stellar sources like gamma rays, X-rays get blocked by the atmosphere. It won't allow things to come to the earth. Visible, there is little bit gap where the visible lights can come to the side. And radio is a region where there is no real opacity. That is why we use radio waves for all the communications, the mobile, TV. We use radio waves because our atmosphere doesn't attenuate those waves. And as you go to further wavelength, further far away wavelengths, again, if you want to study the sun either in any of this gamma ray, X-ray, ultraviolet, or infrared, or any long wavelengths, the only option is to go to the space. The next question is, do we really need to study the sun in gamma rays, X-rays and all? Why not just study it in visible and radio and be happy with it? Why you are interested, or why we are interested to study it in X-rays and gamma rays? That brings to the point that to understand something, okay, I don't know. I think all of you, I have shown this in many talks, and I'm sure many people have shown this. It's like this, blind men seeing the elephant. You put blind men and tell them to go touch the elephant and come back and report, like we do in science. Each blind man will think it's different parts of the elephant. Somebody will think it is a snake, somebody will think it's a tree, somebody who touches the stomach will think it is a wall, etc., etc. And if you call them for a conference, come back and discuss, they will all come back and say, report whatever they saw. And like we do in science, somebody collate all their observations from different studies. What you get is some elephant like this. It's still not very close to the elephant. It is better than saying elephant is a snake or a wall. It is much more closer. So you need to study further. So you need to go to more detailed study, etc., etc. But the point here is that if you have only one viewpoint, what you see will be totally different. What you see will be any of these. When you have multiple viewpoints, at least it is closer to the feature, though it is not perfectly. To get the perfect one, you need further studies. Maybe you put 1,000 people to touch the elephant, then it may come closer to the real thing. So the point I want to say is that the sun is also like that. This is the sun what we see from Earth. The nice sun from the beach, what you see. And sun in UV looks like this. You see there's a difference here. This sun is what you see, the rising sun, the setting sun. Whereas this is the sun when you study the sun in UV. This is real image taken using a satellite called Solar Dynamic Observatory. And it is taken in a wavelength called 1700. It's taken on this date. I just took some random date. Of course, you can see the similar image of today as well. And the same sun, the same day, you can see here, looked in 171 nanometer, it's a different wavelength. It's a totally different sun, 171 angstrom. So you see that it's a different sun. And in different wavelength, it's a different sun. So this is the magnetic field measurement. I just want to put together. Look at this, there is magnetic field, there is sunspots here, it is matching. But you look at the sun in different wavelengths, see really different. It's just like the elephant studying. You see, somebody would have studied, like if you study the sun only in visible radiation, what you see is this first one. Somebody want to study in ultraviolet, you see a different sun. Those two, if they don't know each other, they may argue that there is person on the visible will say there is black dots in the sun. The person who studied the sun in ultraviolet will say, come on, there is no black dots on the sun. Wherever there is magnetic field, you see bright things on the sun. Because in ultraviolet, those regions look bright because they emit a lot of ultraviolet. They emit less visible light, but they emit a lot of ultraviolet. It looks very bright in ultraviolet. You can see here. So to understand what is really happening there, you need to study the sun in all wavelengths. And if you want to study the sun in all wavelengths, only option is to go to the space. You cannot do it from Earth. Okay. Also, there are features like solar flares. You can see here, this is also a real video. It is just huge energy release from the sun, and it is throwing the material out. The material mass of that material is almost as big as Earth's mass. And just imagine the gravity. The sun, I already told that the sun is much more massive than almost 3 lakh times than Earth. Obviously, the gravity will be much higher. Just to send a small 1000 kg Aditya satellite up, we have to spend so big rocket PSLV XL. So imagine the energy required to throw so much material out, how much energy it will be required. It's like millions of atom bombs going off at a time in a small moment. Why is this happening? How is so much energy released? Where is that energy source, energy conserved? So this energy would have been there somewhere. These are all questions which a lot of interest is there and many people are working on. A zoomed in thing of the same thing. So it's just unbelievable that sun, so much energy is released in, this happens all in 10 minutes, 20 minutes time. In 20 minutes time, so much energy is released. Where was this energy before stored? And how is it releasing suddenly? What is causing this release? These are all questions which has a lot of scientific interest in. These are things called solar flares, and this going out of material is generally known as coronal mass ejections. Okay, this is the same video. I just want to show. In 1945, actually all this became very interesting because in 1945, there was a big eruption happened. And you all know that 1945 is a time when World War was ongoing or just ending. So there was a huge eruption and which caused a lot of communication problems to the fighting jets, or because the communication was through that. What happens is all this material which is thrown out from the sun, because you know it of course comes to us if it is thrown us towards us, because we are so close to the sun compared to the astronomical scales. So all this big chunk of plasma comes to the earth and it causes a lot of things what we call a space weather. It causes a lot of disturbances in our space. And it causes a thing called aurora borealis. People who have traveled to higher latitude countries like Norway, Ireland, or Nordic countries, etc., would have seen something called aurora, which is because of that. So these fellows cause a lot of atmospheric disturbances, which directly affects the human life and the industry. That is what I was saying, that it is not just academic interest or scientific interest. There is a lot of interest for governments, different industries, especially the aerospace industries or the airline industries, or people who uses things like GPS. There is the GPS can cause a lot of error if such flares happens. So there is a lot of interest in the community, the bigger community outside scientific community also, to understand what is happening on the sun, when such things will happen. Can we predict? The situation is that even now we cannot predict when exactly a flare will happen. And they say, like the Big Daddy flare, which I showed earlier, if a similar flare happens right now, the loss to the human beings will be much, much higher, because in 1905, there was not much investments on space. There was not much things on space, whereas now every country has lots of satellites and things on the space. All of them will get seriously affected if such big flare or CME happens in this period or in coming days, because it is increasing day by day. And this is very old news. You see, 1882, Telegraph reported storm of electricity came from skies. They don't know where it came from. And it caused a lot of electrical disturbances in high latitude countries, of course. And it just caused power cut, power failure, etc., etc. And this is much more later. They say stock markets crashed as something came from sun. And even now you see, even today's Google News, you open and see, you will see people talking about solar flare coming, frying the earth, etc., etc. Though some of them are a lot of exaggerated, not real, but still big solar flare can cause serious damage to our space things. Though lower latitude countries like India may not be affected much, but our space investments and space assets will definitely get seriously affected. Another point is this atmospheric seeing means even in visible radiation, you go a lot of problems with study from ground or seeing. So you see that is why most of the observatories are kept on top of hills. Okay, so all I wanted to say is that I was trying to bring the motivation why we want to go to space. Another thing for us is that you can continuously study the sun, means there is no nights. If you are around Earth, there will be eclipse and there will be nights where you will not be able to see the sun. Whereas if you go to a point where away from Earth, you will reach, you can study the sun all the time. Considering all this, the best point to go is L1. L1 is a Lagrangian point. What it means is to take any two-body problem with certain conditions of the mass, the ratio, etc. There will be different points, actually 5 points, which are known as Lagrangian points. Since you are all physics students here or physics enthusiasts here, I think I can show this left picture more clearly. So the left picture, what you see is potential field lines. I think all of you know what potential field means. What it means is that if you leave a what is a particle, gravitational particle here on this line, it will follow that particular line. That is what a potential field line means, right? The force will be along that potential field line. So if you leave a particle somewhere here, for example, the first line, it means that it will go around sun because the potential field lines is around sun. So these are the orbits. If you put anything below this, it will just fall to the sun. Whereas these are the regions where it will just go around the sun for a long time. Of course, there will be some perturbations, it can change, etc. But generally, it will follow this line. And if you leave something around Earth, it will start going around Earth. That's what we do for all our satellites. When our moon is doing the same, moon is on this line and it will just go around Earth because the potential field line is like this. Now, there is some points where this potential field line go or there is no, you see that they disappear. Means if you leave a particle in that point, it has no place to follow. It will just stay there. This L4, you can see that it is a region where if you leave here, it will just lay there. This is a simple MSc level project any of you can do. All of you need is GMM by R square and MV square by R, the centripetal force and the gravitational force. Nothing else you don't want to know. You write a small computer program calculating all the distances, the combination of MV square by R and GMM by R square, and start drawing these potential field lines and you'll start seeing this. It is no big science involved here. I think if there are teachers attending this talk, you should try giving this as a project to your students to make a small program and draw such figures. It will be very interesting. And it is very intriguing that what happens at L2, L3, where both bodies are one side, but still it will just stay there. It will not move. If you leave something at exactly at this L1 point, it will simply stay there. It won't go anywhere. It just stay there. It just stay there and observe. It's a very nice point to study the sun. Similarly, L2 point, what you see here, is also an interesting thing if you want to avoid sun and study the deep space. So you would have seen the recently launched James Webb Telescope, JWST, that is placed in L2 because sun is a disturbance for them. They want to look at deep skies. So your best place to go is L2 and just leave it there because it won't move and it will just stay there all the time. And it will go along with Sun Earth, of course, because this is virtual points created because of the two gravitational fields. As Earth goes around the Sun, all these points also will rotate accordingly. So that is why L1 is very interesting for solar observations because you can, if you place satellite here, you can study the sun all the time. There is nothing in between. Of course, Venus and Mercury is in between, but they are very small dots that can't create any big shadow on the view. So that is what the L1 of the Aditya L1 means. And I will. You might be knowing that what eclipse. I think all of you would have seen eclipse. When moon comes in this line between the sun and earth line, called ecliptic line in our jargon. If moon exactly comes in this line, moon crosses this line, not directly on this line, but on both sides during all the new moon day. But when it comes exactly in the sun earth line, what we see is eclipse. That is what when we see eclipse. And when eclipse comes, people started seeing a different things. Normally, sun, which I showed earlier, it was just a round ball. But when an eclipse happens, you start seeing all these things around, which is called the corona. And that itself is so beautiful. You see all these chromic colors, which is reddish-like features, and you see very hairy-like features around, and which looks very beautiful. I don't know how many of you have seen an eclipse. If you get a chance, definitely go and see. This phenomena is only for few minutes or few seconds sometimes, but you should not miss chance to see this. It's really beautiful. And very interesting because the plasma density here is almost 10 power minus 12 times of whatever you see earlier on the sun disk. But the temperature here is much higher. It is very high temperature, almost 600 times. I'll come to that. So it's very small plasma density, but very high temperature. And this emits a lot of UV and extreme UV and X-rays. It emits in X-rays means the temperature is very high. You can see generally in physics what we studied, as you go away from the source, temperature should reduce because it is of the 1 by r square relation. So there is 1 by r square relation, it will reduce. But interestingly, on the sun, after some time, the temperature starts increasing. The black body spectrum starts shifting towards the higher temperature side. It's not really black body spectrum, I should say. It's the thermal radiation, the thermal emissions coming will, here the thermal emissions were all in 5,000 Kelvin, whereas as it comes to far away from the sun, called corona, it comes to almost million Kelvin. It's very interesting why it happens and still not clear. And this corona also looks really different. You see some eclipse, these are all eclipse photos, real photos. On some years, eclipse looks like this, and some years it looks like this. That is also interesting why there is different types of corona, what is happening. And now we know it is because of magnetic field, but it is very interesting because this is connected to the solar cycle. The way to study this, you cannot wait for an eclipse all the time to study because eclipse may happen once in a lifetime. So if you want to really study that, you need to artificially create this eclipse all the time. And the way to create an eclipse is to have a coronagraph. You put an occulter, as you see here, on the way, instead of moon, which is becoming an occulter, you create an occulter and put it here on the wave. That is called a coronagraph. So Aditya L1 started the coronagraph initially. The first plan was to start a coronagraph. Later, they realized that if you are anyway making a coronagraph, why not add more payloads onto this? So the first one, with the big one here, is a coronagraph called visible emission line coronagraph. And there are other instruments, I'll come to them. There is a solar ultraviolet imaging telescope, which I worked on. And then there is Swiss steps, which are all called particle monitors. Then there is a plasma package analyzer. And there are 2 X-ray studying instruments. I'll come to that. So these are the instruments, the real photograph. You can see on the top, there's a big one. This is the visible emission line coronagraph. And the small one next to that is the solar ultraviolet imaging telescope. So this images the sun in ultraviolet. I'll come to the details. And there is a small opening here, as you can see here, that is where one of the X-ray payload is. There is another X-ray payload here. And there is on the other side, other instruments. This is the same image, actual image on the tip of PSLV. So what you see here is the PSLV PS4, the stage 4, and satellite is kept on the tip of the PSLV. Actually, though it looks like a floor, it is not a floor, it is a dummy floor. The rocket is there below this. And this is a heat shield which is about to be closed. And it's very amazing to be on the top of a rocket, but it's such a huge structure. You can see a person standing here. In fact, I was lucky to be here on this time when this photograph was taken, but I'm not seen here, I'm on the other side. But you can compare the size. There is a human being here, and you can compare the size of this with respect to a man. Give an idea. So we are planning it to keep it in a halo orbit around L1. Halo orbit means it is not just kept at L1. It will go like this, what you see the orbit here. There are multiple reasons for that. One reason is communication. If you keep something at L1, as you can see here, if you keep some satellite at L1, there's a big communication problem because sun emits a lot of radio waves, like what we use for communication. I told already radio wave is used for communication. Sound is a big noise of radio waves. So if you put any antenna, I don't know if you have any antennas at your dish antennas or even your home dish antenna, you adjust the dish antenna and just show towards the sun. You will see a lot of radio waves coming from there, and it is a very noisy place. In all wavelength it emits. So you don't want to put, nobody want to put their dish antenna towards sun. So if you place a satellite here at exactly L1 point, you won't be able to communicate it with it because of the big noise called sun at the background. You won't be able to communicate it with. So only if you want to communicate with the satellite, of course, satellite is going to observe the sun images. We want to download it, right? To download those data to Earth, we are using radio waves for communication. So you don't want to keep it at L1 because you cannot communicate it. So you have to keep it little height away so that you point your antenna. So if you are here, you don't want to point your antenna in this direction because it will be very noisy. You want to point it at some point away from the sun at some angle, so that you can avoid sun in your antenna's field of view. So that is why we are placing this. In fact, there are other satellites placed by NASA and ESA. They're also kept in a little hollow orbit, because now you can see here, you can of course communicate with this. If you have an antenna or when it is here, you can communicate with it here because sun won't come in your field of view. That is the point. So it will be kept in this orbit and it will go around L1. Like if you see that potential field lines, it will just follow these lines. This is the actual trajectory of the Aditya L1. We make multiple rounds around the Earth and we are going here. So right now, the current status as of today is on the way. We have made these greens are already completed ones. We have already made 5 rounds around Earth. Each time we increase this apogee, and at some point we fired the thing so that it escapes Earth's gravity, and it's on the way to L1 point, and maybe early January we will do this. Engineers will fire it and do a L1 insertion. Expected that around early January it will reach L1 point. Okay, so coming to the instrument, I told that I'll just briefly touch upon the instrument. I don't want to go to the details because I don't know whether this crowd is very much interested in instrumentation. If somebody is interested, I can definitely answer that after this. So there is visible emission light coronagraph, as I told earlier. Then there is ultraviolet imaging telescope. And then there are 2 X-ray payloads. These are remote sensing payload. The first 4 means sitting at L1, we look towards the sun and study the sun. Whereas 5, 6, 7 are called in situ payloads. They measure things at L1 point or at the orbit where the satellite is going around. So the one is measure aspects, basically look at the particles, which is electrons, protons, ions. And plasma analyzer package will also look at high energy, fast electrons and other plasma properties. And there is a magnetometer, which basically measures the magnetic field at the orbit at the L1 point. So basically, this will study whatever is happening on the sun, and this will see what is happening at L1 point, which is around 15 lakh kilometers from Earth. So this is a cloud view, just to give you a better picture of what I was just talking about. And similar coronagraph, which was launched earlier by NASA called SOHO, has created such images. You can see it's so beautiful. Sometimes you can see some comets going and falling in. It just accidentally happened. You can see here and all. So you see things, there is a lot of emission of particles. And I remind you, throwing out a material from the sun outside is not easy because gravity is so high. It has to overcome the gravity and move, which means the energy of that blast is so high. So the current situation of other instruments which are studied, the SOHO LASCO 2, you see such images. So you can see it is covered the whole thing. And what you see is here. LASCO C1 operated only for very small time. And this is some ground-based telescope. So you can see there's a difference. And the actual eclipse is this. You look at the difference. This is what I wanted to wanted you people to appreciate. This is what is nature's created coronagraph. when nature brings moon on the sun earth line. How beautiful is nature's creation of a coronagraph? This is what the corona, what you see when eclipse happened. These are the human or artificial coronagraphs. We are nowhere near to the nature in perfection of having a perfect occulter. The reason being, our occulters cause a lot of scatter, etc. Whereas moon won't cause any scatter because it's an external occulter. There are reasons. There is a lot of effort these days to create a pattern flying of two satellites, one satellite having camera and another satellite becoming occulter, to bring it closer to the real eclipse views, but we are nowhere near that. So the one R0 is a radius of the sun. The 1 to 2 radius of the sun is quite very little studied, the closer to the sun. So that is where our study will be mostly. And it has a lot of interesting science to do, especially those coronal mass ejections, which I was showing the direction of its motion and the properties of that region, etc. This is, we are expecting, this is an eclipse photograph. On that, our VLC will be observing this region, which is up to 3 R0. And it's also doing spectroscopic scan in this region. I think some of you know how useful spectroscopy is in getting the temperature of this region, getting the plasma properties, the material abundances in the region. You can get many things from that spectroscopy. So this region spectroscopy will be done, zoomed in view. So basically, it will be studying the diagnostic of corona and the dynamics happening there, especially like thing. And also it will be doing some magnetic topology at that region because it has a polarimetric package as well. I don't know how much I can go to these topics. Since it's physics crowd, I thought for spectroscopy, if you observe two spectral lines, there is something called line ratio. You can take a ratio of the two lines because this line formation has something to do with temperature. By doing this line ratio technique, we can get the temperature. So this is a simulation study using a KNT which you can see, you can get an idea about temperature versus this emission ratio. By using this curve, temperature with emission calibration curve, by actually observing this line ratio, you can deduce what is the temperature in that region. So that is a technique VLC will be using. There are two cameras, one will observe in red wavelength, another in green. And the exact wavelengths are given here. And using these two wavelengths, you can get an idea about the temperature and temperature features in that region. Let me just move this fellow out. Okay. So this is something which has been studied earlier also, 789.2 and 530.3. We will be observing in the same red and green curve in VLC, and it will give you quite good idea about how the temperatures features are, etc., etc. So these are eclipse observations. People have used this during eclipse. I told you eclipse is for a few minutes. You cannot study much. Whereas we are going to observe it 24/7 all the days, all through 365 days. So that's going to give you a much better idea about what is happening corona during all through these years. Another instrument is solar ultraviolet imaging telescope, which is close to my heart because I've worked on this for almost for 5-6 years continuously as a project scientist in developing this thing. So you saw already that in VLC image, the center part is missing because this is occulted. We are blocking that region. So it will study that disk of the sun in ultraviolet range. So it is in 200 to 400 nanometer, and it will provide near simultaneous coverage. And it is very unique because it's not much studied. This region is something which is not well studied, and it will give you a very nice context to the VLC. And it can study many things related to solar flares and all. I'm not going to the details of these things because I think this crowd may be a general crowd that way in physics. If somebody is very much interested, I will, in the question answer, I will come back to this section. So, you know, I already told there is different layers of the sun where the temperature profile suddenly increases and density falls. So on this solid line is a temperature line. The x-axis is the height, y-axis is the temperature. You can see as the height increases, temperature reduces, but at some point it increases suddenly to million Kelvin. And it leads to different layers of the sun called photosphere, chromosphere, corona, etc. The suit will be studying, this is a black body spectrum of the sun. The suit will be mostly studying this region, which is called the photosphere and chromosphere. We will be studying this region before where this temperature increasing starts, but before the major jump. So this is a region where our instrument will be mostly focusing on. It's called visible and visible region and ultraviolet region. Whereas this region will be mostly emitting in extreme ultraviolet and X-rays. This is sun in different images, which I showed in the beginning. This is the region we will be studying, which has very limited observations. This region is quite well studied these days. I showed you those images from an observatory called Solar Dynamic Observatory. So that has been quite well studied. So, UV emission directly interact with atmosphere. And so it's very important to study the UV emission from the sun. It affects the chemistry of the atmosphere, like ozone formation. It also might affect our cloud formation, etc., which is still not fully proved. It's a topic of debate. And of course, all the ultraviolet coming absorbed by atmosphere, it is a very simple logic by conservation of energy that if atmosphere is absorbing the ultraviolet rays, this energy is going somewhere. Atmosphere is doing something with this energy. Energy has conserved. We all know that energy cannot die, cannot destroy. So all this energy deposited by ultraviolet atmosphere, what is happening to that energy is an interesting topic of research. And combination research we should do, physics community should do along with atmospheric studies, people who study stratosphere, etc. Okay, these are the details about the telescope. I think many of you may not be interested in that. So it has two mirrors basically. There's a primary, secondary, and there are filters which chooses the different wavelengths. And we have a camera system here which takes these images. If you, on the VLC expected image, if we impart suit, it will basically come something like this. These are images taken from other satellite, but it will be like this. So we can get the full picture of from the sun disk to 3 R0, combining these two, VLC and suit. And suit has some overlapping region because the field of view of suit is this yellow line. We can think of some combined science with VLC and suit. So that is why this Aditya become unique compared to some other missions, because it is sort of an observatory class satellite where there are multiple complementary instruments which can complement each other in studies, and combined data product will be very useful. Again, these are specs. I will skip some of the specs. So as I told you, there is a coupling between the atmosphere. I already showed you there is magnetic field. It will look dark in photosphere, but it creates bright features in atmosphere. So how is this magnetic field coupled through the plasma at different heights? So this MHD, which is magnetohydrodynamics, how magnetic field couples with plasma, it's a lot of scientific interest in that, and this data will be one of the unique data to study multiple layers because we are observing at different heights near simultaneously. Then these solar flares, which I told you earlier, these are sudden emission of energy. You can see here. You see here, if you look at here, this is time. Crashed or what? Okay, I think you can see the screen. Okay, so you can see there is a sudden increase, almost 10 power. This is watts per meter. The jump is almost orders, around 100 watts jump. Huge lot of energy which is being released suddenly within a small time scale. It's like half an hour. This is 10 o'clock at night, and this is 11 o'clock at night. By 10 to 10:20, it has released so much energy suddenly. These are called solar flares. And there is a lot of interest in studying solar flares because the flare look differently in different wavelengths, etc. I'm running out of time. Maybe the details will come if there are questions about this. So there is a lot of questions. I wanted to address some of them. If there are students who are interested to do research in this field, who are curious to study about solar flares, you might have read about them in different newspapers and all. These are just few of the questions I just typed in about unanswered questions, which is a hot topic of research, just about solar flare studies. how flares related, and many of these things might be answered with Aditya data. I'm not saying will be, it might be, depending on how much effort we put, because it involves a lot of modeling, there is a lot of theoretical work. Aditya will give you observational data. So combined effort might produce answers to some of these long-lasting questions. There is also a very interesting thing about solar radiation altogether. What you see here is wavelength on the x-axis and solar irradiance on the y-axis, which is seen in blue, and green is on the right side axis, which is the ratio, the variability of spectral variability, how much this is changing. If you just focus on the blue and red is the black body fitted curve. If you just focus on the blue color here, this is how the radiation of the sun comes in a normal radiation. The sky blue color is at 0 kilometer, means that our sea surface, what we call as the surface of the sea, there is a lot of absorptions on the sky. That's why these absorption lines are, some energies are absorbed. So this is what reaches us. You see that all the UV is cut off because UV won't reach us. From the sun there is UV emitted, but the sky blue you can see that you won't reach our surface. Now, if you look at the green, which is a variability over time, this is there is a different x-axis here, which is variable. This is x-axis is wavelength only, and y-axis is variability over a solar cycle. Written here, maximum minus minimum by minimum ratio. You see this 11-year cycle, which is one solar cycle. Over 11 years, you find maximum emission by minimum emission. Maximum emission minus minimum emission. That is what the green gives. If you look at the green, the variation in visible range, what we generally observe, is very small. It's not very big. But the variation in ultraviolet and X-rays is very huge. The variation happens mostly in this region. Hence, it is very interesting to study what is happening in ultraviolet. And if something is affecting our atmosphere, like stratosphere, or if something connection with our climate, any sun-earth connection, this region may not contribute much because this is quite stable over many years. But this region is the one which is a varying component. If something is happening, the varying component is the one which may contribute to that variation, the changes in our climate or atmosphere. So that is why we decided to study this region, which is a varying region. That is why there is a lot of interest to study the UV region and, of course, X-ray regions, etc. So this is a region solar ultraviolet imaging telescope will study. And because I told you, this is a region which has interact with our atmosphere, especially upper atmosphere, and deposit that energy. We also have two X-ray instruments, which is Solex and Helios, which basically look sun as a star and study the emission from the sun in X-rays at different energies. I'll show you that energy. These are the existing missions, and if you see energy from the observation, and this is energy resolution, you see that existing missions, there is a big gap here with respect to energy and energy resolution. So our two instruments, Solex and Helios, will fill mostly this gap. So these are the two instruments on Aditya which will be having decent energy resolution and cover a large area of energy. Combining all the four, we can do a lot of science. As I told you, since this is an observatory class mission, you can do combined science, combining all the different instruments, because all of them are studying the sun at the same time. There are 3 in situ instruments also. I will not go to the details. I am already running late of an hour. Because it's a new topic, I thought I should give some that bigger introduction. Sorry for that. So it basically measures the particles at L1 and the magnetic field at L1. The science of that, I will not go to the details unless there is specific interest about that. So as I told you, there are a lot of questions and many of them could be answered in this with Aditya. And if there are students, you are all welcome to work on this. And I would say, as I told in my abstract also, this is a golden era for students who want to enter into this field of research, studying the sun and sun-earth connection, because we are going to have our own data and a lot of data availability, and that all we need is more brains, because there is a lot of data, there is a lot of computational facility these days to do theoretical work and modeling. All we require is more brains to put on this and spend time on this and solve some of these long-lasting problems. Okay, I'll end here with a nice movie. Meanwhile, you can ask your questions. I will look at the chat box. So you can switch on your mic and ask questions. Meanwhile, at this beautiful movie, this is a real video of the solar emission. You all can enjoy the real one. It's not any artistical impression. Okay. Those who want to type the question can type in. For those who want to ask questions can turn their mic and ask the questions. I leave it to the moderator. I don't know what is the process. And here, Ratul, over to you.
Okay, thank you, Sreejith. Thank you very much for the nice and very informative talk. Now audience can ask questions. Please unmute and ask questions. Okay, so I have a question, Sreejith.
Sure.
Okay. Actually, when we calculate L1 point, do we need to consider the gravitational fields of other planets and in your plot
Okay.
you have shown sun and Earth.
Okay. Okay.
But there can be other planets.
Yeah. See, ideally, you should consider all the gravitational bodies. Technically, you think in an ideal situation, but it depends on how much influence they have. So, for example, if Jupiter can cause any change to L1 point, it might cause because Jupiter is a massive thing. So, if you want to perfectly find the L1 point, you need all the major bodies. At least we need to consider up to Jupiter. Okay, Saturn won't have much influence because it's really far away. You may have to include Mars and Jupiter also. It's a many body problem. But the physics become more complicated when you have many body problem. And the question is whether is it of importance to us, because we are not going to find the L1 at a millimeter level or a meter level. There is no interest in that. Even a kilometer error or a 100-kilometer error is fine, because we are talking about 15-kilometer away and our orbit is mostly 3 lakh kilometers. In that, an error of 100 kilometer or 1,000 kilometers is fine. So for practical purposes, for any such thing, and there is similar L1 body between Earth, Moon also. Any two body will have a L1, L2, L3, L4, L5, right? Gravitationally. So what I'm trying to say is that it depends on your requirement. If somebody is particular about finding it with a meter accuracy, maybe you have to consider all the many bodies. But if your practical requirement is not that stringent, maybe two bodies are enough.
Okay. I just want to add that, I mean, if people want to talk, ask questions in Malayalam, so that is also fine. Okay.
Yeah, free. You can ask in Malayalam. I can perfectly understand Malayalam and speak Malayalam.
Sir, I have one question.
Sure.
Can I build it? So
Yeah.
we already have a image like a STO or it's another one what we from ESA. SOHO also. Okay. So they also
Yes.
image from the UV or EV band range. How our suit
Yes.
is different compared to there, and what some extra science what we can able to do from this Aditya L1 compared to them.
Okay. Okay. So it's an interesting question. The difference is that suit is first of all not a EUV instrument. The SOHO, which was earlier there, which had, okay, maybe I can show you that. Okay, there are 4 instruments at L1 right now. There is a SOHO which is decommissioned right now, but it provided a lot of data. And there is something called ACE and WIND, which is mostly particle monitoring and solar wind monitoring, which is in situ measurements mostly like our in situ particles. So this will be a good comparison with that. And there is a Discover as well there. So Aditya is going to be, you can see a red color here. These are all kept a little far away because of the same reason. They all make an orbit around the L1. I already explained that. SOHO is the only one which we can compare with. And SOHO did not have a UV instrument. It was having a EUV instrument. And of course, after the SDO, there is a lot of EUV studies. I showed earlier that the EUV part is quite well understood these days. The real physical problems on the sun is not solved, but we have enough data to solve them because we have a lot of EUV observations. But the near UV is, there is no instrument which has been flown. There is an instrument close to that in the solar orbiter, which is recently launched by European Space Observatory, the ESA. But the problem with orbiter is it is having a very long ecliptic path. So it comes close to the sun, it goes very far away for their own scientific purpose. Basically, they are studying the heliosphere. So it switches on this UV instrument only when it comes to certain things. So it is very limited time only they operate that. Rest of the time they are not operating it for their practical purposes. So there is no instrument on space. On ground, there are some H alpha instruments which study chromosphere, but there is no UV instruments. Of course, you cannot have UV instruments on ground. So in reality, there is no instrument right now which study the sun in UV. In fact, there was no instrument also which studied in detail. There are some IRIS, for example, there is a payload satellite which observe part of the spectrum, like magnesium. It's a spectroscope. It's a grating-based spectroscope, slit spectroscope. So it can do a raster scan of a small region and very specific wavelengths, covering a small specific range. So that is the only one which is, in a way, which is closer to our range of spectral range. But it has its own limitation. It is very good spectroscope because it is great slit based, but it has limitations like it can only study a smaller region at a time. And raster scan cadence is very poor because it has to do raster scan, etc., etc. So that's why it becomes very unique at this point of time.
Thank you, sir.
More questions? Okay, Sreejith, I want to know the opportunities in ISRO for BSc and MSc students, whether they can do some projects there or at least visit and understand the things. What are the instruments? What are the things going inside? What are the opportunities for that?
Okay, I'm not an ISRO person, but I have a long association with them, including I did PhD there, etc. So there are two major physics centers directly under ISRO. One is Space Physics Laboratory in Trivandrum. It's a part of VSSC. They mostly study the atmosphere, Earth's atmosphere, and mostly atmospheric as the space physics, basically. And there is a space astronomy group in Bangalore as a part of the UR Satellite Center, who mostly does the astronomy and planetary science. So these are then there is, of course, Physical Research Laboratory, the mother of all space research, which is in Ahmedabad, which comes under the Department of Space. And there are many other astronomical institutes around the world. Around India, IAA is there, IUCA is there, and including our center. But under ISRO, majorly, these are the two groups I can immediately think of. Of course, you can visit them. They are all astronomers like any of us, done PhD different places, postdocs, etc. You can try to contact any of them. You can find their details in, I think, their webpage or somewhere. And you can write to them. You can visit their, since they have some high security restrictions and all, you may have to take prior appointments and create gate pass and all. You can also do MSc projects there. I know many people, even from Kerala, I saw even last year also, many people did. You can contact them. There are 2 years, like your summer vacation time, if you want to do a project, you can approach the scientists there, and if they have problems, they will be happy to host you, and you can do projects there. And PhD program also they have. SPL Trivandrum has a regular PhD program. URSC is also having, their intake is a little less these days. But right now they have some 3-4 PhD students there this year joined. So they don't recruit through normal entrance examination. They have their own advertisement calls. You can have a look at that and apply for that. They conduct their own interviews and they take students. So they have, just like any other research institutes, almost everything is there. Only thing is there is more security control. You cannot just walk in like other places. Like our place is somewhere you can just walk in like a tourist, or even IAA or IUCA, you can just walk in. But these places you may have to take a prior appointment, etc. That's the only difference. Otherwise, everything is
Sir,
the
what
same.
is this question, sir? Sorry to interrupt you. What is this question? I am from ISRO only. What is this question?
Okay, this is asking the opportunities for students to do project in ISRO, in astrophysics or the topic of research.
Yeah, yearly actually they will on website actually they will give the advertisement. So based on that they have to apply, sir.
Yeah, exactly.
I am from Bangalore unit only. You are a satellite center.
Okay, okay. Which division, sir?
I am from mechanism, sir. Spacecraft mechanisms group.
Oh, okay, okay.
All our mechanisms, everything, door opening and all those things we only will do.
Yeah, yeah. Yeah, I know. I've been there. I know Narendra, everybody. Shamrao. Your good name?
Yeah, yes, sir. My name is Rajshekhar Babu.
Oh, okay, okay.
I'm working under Narendra sir only. Actually, he's my division head.
Okay, okay, okay. That's our DPD for Aditya.
Right. Aditya L1 also mechanism DPD. Yes, sir. Thank you.
Okay, thank you very much, Rajashekhar, for joining us. More questions? Okay, there is a question in chat box by Deepak. Can you speak a bit about AI on board Aditya L1? Asking about AI.
Okay. No, okay. The difficulty is maybe something which I have talking to my students here. See, the computation on board is not easy. We cannot send a normal PC to space because it won't call. It will just fail because there are multiple things. There is a lot of radiation out there, and it can just kill the normal electronics what you send. So the electronics, whatever you send on a satellite, has to be made sure that that can survive on space. The reliability on space is very important. So the computational assets on board is not equal to the computational assets on ground. Here you can have unlimited computation, but on board it is very, very limited. So if you look at the computational power of Aditya, which is the current age, will be almost equivalent to the computer which was on ground maybe in 90s or 80s or 90s. Because you cannot send just a normal computer to the space just like that. So there is no AI on board right now. Because you need a lot of computational power for AI. But the data which Aditya L1 produces and comes to the ground, all of us are using many, not really AI, but a lot of deep learning and machine learning. People are working on that, how to use these computational methods to analyze the data more efficiently and dig out the science or the required things from the data. But this all happens on ground. There is nothing on board. There is some onboard intelligence. Even we had a paper recently on the onboard intelligence. We have some intelligence, like we have some flare trigger finding, etc., etc. But these are all very, very basic stuff, not really to the level of an artificial intelligence as defined by us right now. Maybe whatever we have is an artificial intelligence of 90s. Is that all clear, or you need more explanation?
Okay, he says thank you. Okay, thank you, Deepak. And more questions? Any more questions, comments? Okay. If there are no more further questions, maybe we can thank the speaker again. Thank you very much, Sreejith, for your time and a very nice talk. We hope to collaborate with you in future also. Thank you very much.
Sorry, I overshot a little bit because I thought maybe new topic I should. Anyway.
Yeah, it's okay, no problem.
Thank you for hosting me, Ratul, and the theoretical physics community of Kerala. Yeah, please visit us anytime, and we can, of course, discuss interesting science. And if there are students interested in these topics, please contact any of the solar astronomer in the country. All of us are involved with this mission some way or other, and they can any of the more space physics people also. They all can direct you to this topic, and there is a lot of things can be done at this time. This is the right time if anybody want to do enter into this area of research.
Thank you, Sreejith, and thank you all the audience. I think we can wind up.
Okay, thank you, Ratul.
Okay, thank you.
Yeah, thank you all.